Good morning, everyone. Today, let's talk about AC analysis of resistors, capacitors, and inductors. Okay, so same RLC circuits, but applied with an AC source. And then if you have any questions, let's have an open session. We can get your questions answered. Okay, homework 17. Transfer function. Oh, so that's 6. Let me, let me open up the website and I want to take a look at the due dates. Let's see. Just make sure that it's not. Was it due this weekend? Okay, so I'm going to extend that. So that is chapter 6, transfer function, and we can certainly look into it too. I just want to see. All right, EE201. Let's bring it on this side. The second one. Do you have 3 terms in your output? The frequency for the third one is omega is 15,000. And if we look at the graph, the transfer function, the value at 15,000 is 0. So the third term would be 0. Frequency would be 7,500. I think at 7,500, the value of the transfer function goes to 0. Let me open it up so then we have a clear picture of the question. All right, assignments. All right, transfer function is due today. Filters 12th, 17th, and 21. We have time. I think I'm going to push these homework back by a couple of days. Okay, let's see. Yeah, launch 6.8, right? Okay, 6.8. Okay, so 7,500, the value is not 0. Sorry. So let me take that back. It's not 0. So in this case, to find the actual value at 7,500, we need to do a little bit of math. So at x equals 0, the value is 2. At x equals 10, y equals 1. So we need to find the exact value at x equals 7.5. What value do you have? 1.25. All right, let's see. So from 2, it's going down to 1 over 10. And so over 5, it should go down half. And 2.5 should go by 1.25. Okay, so 1.25 is correct. And 1.25 and V in is 2. So 2 times 1.25. So 2.5. Is that your answer? Okay, so 2.5. And then cos of 15,000 pi t. Angle is 0. And 0 plus, what's the answer that you have for the angle? Plus or minus? Minus 135. Which seems about correct. So it's 190. All right, so at 5, it's minus 90. And at 7.5, it would be 135. But let's see. You entered minus 135, right? Try entering 360 minus 135. Try entering plus 225. See if that works. Yes. Have you already reviewed the lecture video and the notes? Okay. So let me bring up the notebook. Let me know whether it works or not, okay? 360 minus 135. So sorry, what? So it worked. Okay. No, no. This is a system. It's not an AI system. So I think whatever answer is like programmed into the system, it simply matches it. And if it doesn't match up, which I think is a flaw in the system, and we should accept both values. But no one has brought it up before. So, all right, let's see. Where did this go? 30621. 18, 19, 20. Today is 21. Okay, so to all students, I have my annotated notes right here. And if we go into chapter 6, there is a solved problem. Let me switch over. Right. If you're attending online, just feel free to speak up. Okay. Don't type anything in the chat because unable to monitor the chat at the same time. But we have good speakers here in the classroom, so just speak up if you have a question. All right, here. This is the homework problem is exactly the same as this. And so I've solved it step by step, including all the minor steps. And so if students view the lecture videos and review this page, they should be able to solve it. Okay. And as I said, I will push the homework back by, let's say today's Friday, right? Let's push it back by 2 days. So I'll make it due on Sunday. That way students don't lose any time. And if they have further questions, they can reach out to me over the weekend. And then the other homework assignments, they can all be. So I'll push all of those back by 2 days too. So filters will be due November 9th, 18 on the 14th. Let's see, which is next month, no, next Friday. And resonant circuits, a couple of days after that, which is the 19th. And then finally power, I'll make due on the 23rd. So not quite before Thanksgiving break, but on the Sunday. All right. And so that way there's plenty of time for everybody. Okay, so 17, 18, 19, and 20, I will push it back by 2 days, respectively, all of them. Okay. Any other questions before I talk about AC analysis? Okay. All right. Do you have any questions? That's the only one. Okay. Do you want to solve it now so that if you have any questions, I can answer them or? All right, let's do, let me copy other slides. Let's see, chapter 5. And are you also taking the lab? How many labs have you completed so far in your class? So 7 and 8 are remaining. Okay. So let me just talk about that also, because they're what are they doing? Have they informed? So every instructor will have their own implementation. Have they told you on what they're planning to do? Okay, all right. So there are two slides here, photo rectangular. Have you reviewed all of these? Okay, all right. So let's just talk about that a bit. I'm going to just copy out these slides. Phasors all the way up to impedance, series, parallel, and those are the examples. Okay, so up to page 16. All right, 5 pages. All right, AC analysis. And then we'll go into the individual pages. All right, so the first thing that we talked about was phasors, right? Phasors are basically vector representations of a time-varying sinusoidal waveform. So in the AC analysis, what we do is we have to solve differential equations. So the math becomes complex. So in order to simplify the math, we perform a conversion. We convert time-varying sources and the impedances and reactances of the capacitors and inductors and represent it as complex numbers, complex quantities. So phasor is basically the source being represented as a vector. So vector representation. And we have already formed the homework on this one, done the homework on this one. Any questions about this? Okay. So typically we don't go over the derivation for non-E majors. But the simplest way to put it is like we have a time varying waveform like this one, right? And this time varying waveform has a peak value. The peak value is Vm or Vp, whatever notation we want to use. So it's Vm cos of omega t plus theta. So 3 different quantities in there. And if we wish to represent it as a vector in the complex plane, so it's a mathematical transformation. That's all it is. And then we represent it simply as Vm with an angle of theta. So now it's a vector representation mathematically, that's all. And the reason we do it is so that we are able to solve the circuits the same way that we did for DC circuits. That's it. And that's the only purpose that we do it. So in order to simplify the math, we are doing this. We're using complex numbers to make it less complex. So sources are represented as phasors. And then when it comes to resistors, capacitors, and inductors, we represent them with impedances. So they also have complex number representation. Let's see. Okay. So let's put a pin in this and go back to chapters 1 and 2. If you go back to chapters 1 and 2, all we had were resistors in the circuit, and we are applying DC voltage and DC current. So for a resistor, when we apply a DC voltage or current, we can calculate those quantities using Ohm's law, V equals IR, right? Then we applied DC voltages to capacitors and inductors, and they had their own equations. But because they're energy storage devices, that energy storage transfer takes some time. And so the voltage and current in those inductors and capacitors are time dependent. And because they are time dependent, when it comes to AC, it requires solving of differential equations. You with me so far? Okay. So that's the only thing right now. So in chapters 1 and 2, we learned about resistive circuit analysis. In chapters 3 and 4, we learned about capacitors and inductors. And in 5, we are going to take resistors, inductors, and capacitors and apply AC sources to them. So to simplify the maths and to not have to solve differential equations, we take the source and we represent the source as a vector, as a complex quantity, so complex numbers. And for resistors, capacitors, and inductors, we do the same. We'll do vector representation. Now, if you try to represent resistors, inductors, and capacitors as a vector for AC sources, well, resistors behave exactly the same way for AC as they do for DC. Okay. AC representation is the same as DC. There is no change. Resistor is resistor, it's R. Nothing changes. Capacitors and inductors, however, again, they're energy storage devices, right? So let's say we have a sine wave like this. And you apply the sine wave to a inductor, or let's say you apply to an inductor. What happens? If you apply a positive voltage to the inductor, it's going into the inductor. So the inductor receives the energy, right? So let's just do positive half cycle. Apply to an inductor. Energy goes in. What happens in the negative half cycle? It goes out. So the exact opposite happens. Energy goes out. In a capacitor, the exact same thing happens, but the cycles are flipped. And so, and I want to represent this as a sine wave being applied. So let's move this down. Okay, applied to inductor and capacitor. So any guesses on what happens? Well, not guesses, but you can take a good shot at answering what happens for a capacitor. So in positive cycle, energy goes out, or meaning it goes back in the circuit. Negative, it goes in. And that's the big difference. So there are differences between a resistor and so resistor on one hand and the inductor and capacitor on the other side. And then further, the inductor and capacitor are also opposite of each other. So they're very similar in many ways, but they're exact opposite of each other. So a little segue. We did lab 6, lab 7, and lab 8. They're all related together. It's all the same fundamental principles. In lab 6, we did phasor diagrams. Lab 6 was about applying KVL to inductors and capacitors. Lab 7 is about frequency response and resonance circuits. And lab 8 is about AC power. But in all three of them, you have a inductor and capacitor in the exact same circuit. Okay, so if you have an inductor and capacitor in the same circuit, actually, let's just talk about an inductor first. If you have an inductor and you have an AC source, energy goes in, energy goes out, energy goes in, energy goes out. Now, if you insert a capacitor in there and the energy comes out from the inductor, what happens? Goes into the capacitor, exactly. And so energy now is bouncing between the inductor and the capacitor, back and forth, back and forth. It's localized. And so when the energy transfer between the two is exactly the same, it's complete, it's like matched, which doesn't happen in real life, obviously. But let's say you have a hypothetical or theoretical system where you have an inductor and you have a certain size capacitor. You apply certain energy to it at a certain frequency, and then energy goes in, out, goes out of the inductor, goes into the capacitor. 100% of the energy is transferred. And that's when resonance occurs. And that's what you'll study in lab 7. Lab 6 was about applying KVL. And so we were simply simulating if you had, there were two procedures. The first procedure was applied energy to the inductor. So there's a resistor and an inductor in the same circuit. Resistor receives some energy, drops some voltage across it. The inductor receives some energy, it drops some voltage across it. And then you created a KVL map. That was the phasor diagram. In the second one, we added a capacitor. The capacitor was there so that it balances out or reduces the need for energy for the inductor. Okay, and so that was the second phasor diagram. So if you recall lab 6 phasor diagram, for an inductor, it went up. For a capacitor, it went down. Okay, so it's balancing it out. Lab 7 is resonance, which is when the energy transfer between the two is exactly the same. In real life, very nearly the same. And so that's when electrical resonance happens. And when electrical resonance happens, the impedances of these capacitors and inductors goes away. It's purely resistive. And that would be in lab 8. So that's a good question. So in lab 8, what we are going to do is we want that power that goes into the inductor to be as low as possible. And so we put a capacitor in front of it. And so that power now goes into the capacitor. And then it just bounces back and forth in there. And so lab 8, we are not varying the frequency. We are looking at energy and the value of the capacitor that is required to balance that energy. Okay. That also ties a little bit into the last chapter, which is AC power. Right? Lab 8 is the last lab. AC power is the last lab. But 6, 7, and 8, all 3 labs are tied together. They're all the same. The only thing is we are looking at different perspectives. Okay. All right, let me take a pause, ask your questions. Okay. All right, so then let's talk about what's reactance and what's impedance. Okay. Pure inductors and pure capacitors do not have any resistance, ideal ones. Okay. Ideal inductors, the resistance is 0. Ideal capacitors, the resistance is infinite. Right? As an inductor, let's say you have an ideal wire. Right? What is the resistance of this wire? 0. But now if you take this wire and wind it up in a coil, spiral coil, it's still the same wire. So the resistance would still be 0, right? But now they're storing energy, right? So both of these devices, when you send energy into these devices, they don't have any resistance, meaning they are not opposing that energy transfer. Energy comes in. Great. No opposition to it. But that stored energy gives rise, let's say in an inductor, it gives rise to a magnetic field. It's stored in the magnetic field. So it gives rise to a voltage, and that voltage has opposite polarity of the input. And so it opposes any change in that input. Same thing for the capacitor. Okay. So let's simplify it. We have an input. That energy input is being sent to the inductor or capacitor. It receives the energy, stores it, but that stored energy is now going to oppose any change in this input. If the input remains constant, like DC, right? Let's say you apply 10-volt DC to an inductor capacitor, it's going to receive the energy, store it, doesn't do anything. But now if you try to change this 10 volts to, let's say, 5 volts or 15 volts, you're now changing the input value. If you change this value, then that stored energy is going to oppose that change. And that opposition is termed as reactance. Okay, so reactance is a quantity that is solely attributed or possessed only by the inductor or capacitor. Resistors do not store any energy, so they do not have any reactance. Let's take a pause. Let me know if you have any questions. Make sense? Okay. So again, resistor only has resistance, does not have reactance. Inductors and capacitors on the other side, they don't have any resistance, but they have reactance. And if we represent this as a complex quantity, then we term that as impedance. So impedance is resistance plus reactance. So, and this is there in the notes in the lecture video. So hopefully whenever you review it, we can represent impedance as a complex quantity, and we term it as a impedance triangle. Similar to phasor diagrams. Again, this is a complex quantity. So impedance of a resistor, impedance is noted by uppercase Z, resistance is R, and reactance is X. So in polar form, we can write impedance Z is R plus X, but the X is represented as an imaginary number. It's not imaginary. It has a real physical basis in real life. Okay. When we say imaginary reactance, oftentimes it sounds confusing. It's not a figment of somebody's imagination. It's simply the mathematical representation. That's all. So R plus JX. Technically, it's just R plus X. That's all it is. R plus X, but it's imaginary number, so R plus JX. Impedance of a resistor is simply the resistor R itself. There is no such thing as ZR. This I use just for explanation purposes. Okay. And then ZL is impedance of the inductor. And the reason they have impedance is because AC input is constantly changing its value, right? So the slower it changes, the lower the opposition, right? The reactance is based on how much the input is changing. So if it changes very slowly, then the impedance or the reactance is low. But if it changes faster, then the impedance is higher. Which means if the frequency of our waveform is higher, or as it goes up, as F increases, the reactance or the opposition from the inductor also increases. Mathematically, it's represented as J omega L. Okay, ZL is simply J XL, reactance, and reactance XL is omega times L, or 2 pi FL. Hence, ZL is J omega L, or J 2 pi FL. ZC, on the other hand, is the opposite of frequency. In a capacitor, you apply a voltage, it stores the energy. Current goes to zero once it's fully charged. But now if you reverse it, as in like if you apply an AC signal, then it's trying to change much faster, right? So then currents starts flowing constantly across the capacitor. So the faster it changes, the more, so the less it opposes. So as the frequency increases, This would be 1 over J XC. As the frequency increases, the capacitor reactance and the capacitor impedance will decrease. They're inversely proportional. 1 over omega C, which is 1 over 2 pi FC. And if the system has all three, meaning you have an RLC system, you have a resistor in there, you have an inductor in there, you have a capacitor in there, then combined effects of all, you have pure resistance, which is plotted on the x-axis, and then your reactance, inductor points up and capacitance points down. So if you have both in the same system, if the inductor has a higher value than the capacitor, then you have a positive X. And if the capacitor is higher than the inductor, then you have a negative, sorry, not positive X. You have a positive, positive reactance. If capacitor is larger than the inductor in terms of energy storage, then you have a negative reactance overall. Okay. And then the hypotenuse is the magnitude of that impedance. So magnitude Z. Is it starting to make a bit more sense? Okay. That's just a mathematical reaction. I mean, sorry, mathematical representation. Okay. We have about 15 minutes left. So do you have any questions or shall we move on? Okay. All right. So this was just polar to rectangular, rectangular to polar operations. I'm guessing you're fine with this, right? Okay. All right. Fundamental laws. We had Ohm's law, KVL, and KCL. All of them still work. Okay. All of them still work. The only thing is everything must be represented as a vector or as a complex quantity. So voltage across a resistor in an AC system, V equals IR. For a inductor, I times ZL. For a capacitor, I times ZC. So Ohm's law still applies. If we were trying to solve this as differential equation, we would not be able to do so. Or actually, we would be able to do so, but not as straightforward and simple as this. Okay. One thing about impedance, reactance, and resistance is that the symbol and the units are all the same. They're all represented by the same resistor symbol. Okay, the same resistor symbol, no difference. So reactance, impedance, and resistance, they're all the same. So they're all ohms. And that is the reason why we are able to combine impedances together. So again, KVL still works. This was lab 6. Okay. Lab 6 phasor diagrams was nothing but applying KVL. We added up the voltages, but when we actually measure them with a meter, we don't have any angle information. We only have magnitude. So we measure the magnitude with a meter, and then we draw the phasor diagram to figure out the angle. Okay, graphical solutions. And that's the whole point of doing this complex math. That's all it is. Okay. Impedances and reactances can be added up similar to resistors. So if it's a series connection of RLC, we cannot combine. So if you have a resistor, inductor, and a capacitor, and you want to find the total ZEQ, well, these quantities are different, right? So just fundamentally, there are 3 different components. So we cannot add R, L, and C. But if we convert them into impedances or reactances, now we can find ZEQ, similar to REQ. So this would be R, this would be ZL, this would be ZC. So then it becomes very straightforward to apply our circuit analysis techniques. Does that make sense? Okay. That's going to be on our quiz on Monday. So you're the only one who's here. Calculations and just understanding what the circuit is and just doing similar to DC. So it's not going to be too onerous. In For EE major students, we do have them do node voltage and mesh current using, for AC circuits. But for 201, we don't do that. Yeah, so there's no node voltage or mesh current using this. The other thing, I'm going to post it in an announcement, but since you are already here and there are a couple of students online, AC analysis, I will assess on Monday quiz, but it won't be on the final exam. Yeah, so few less topics to study on the final exam. All right, so that's impedances in series and parallel. Okay, I think that was the last slide on here. The other one is annotated notes. You can go into, yeah, so the last few pages right here, I go over the example problems. And there are a couple of, there are notes on Canvas under slides where I have a few solved examples in PDF. And so again, I will have all of that in the announcement, and so students should study and look it up. But this is exactly the circuit that I was talking about. We have an RLC in series, and we just need to find the voltages and currents associated with it. So definitely review this on page 20. Okay, these were straightforward. So these 5 examples pretty much cover everything. Okay, so when I did these notes, I did it step by step. All students have access to these notes, and every minute step is covered in here. So basically, students, it's self-explanatory. That's what I'm trying to say. Okay. All right, let's take a pause. Let me know if you have any questions. You have what? In 10 minutes. Okay. You want to get ready for that? Yeah. I can talk a bit about lab 7 and 8 if you want. Okay. All right, then. Okay. Anyone online have any questions? Okay. All right. Well, I guess we'll end class here today. We'll have the quiz on Monday on AC analysis. Okay. All right. Have a good weekend, everyone.